Hello there, this is another lesson for the statistics part of the Further Maths Year 12 course, and you'll notice I've got a picture of a graphical calculator on the screen because the ones I've given out in class up till now have been the Casio Class Whiz, and the Casio Class Whiz is excellent, really good calculator, but it's really good at for statistical reasons, looking at the binomial distribution and also looking at the normal distribution, both of which we've seen. But unfortunately, the geometric distribution, which is what today's lesson is not on this calculator, and you have to have a more advanced calculator, and it's this one that I'm suggesting we're going to use. There's obviously other calculators available. Now, to get onto this, you have to press second function, and then above this button here, you can just see it, it says distri. Obviously standing for distribution, and on that, if you go second function distri, you'll find lots of different distributions, quite a few of which we will use over the course of the 2 years doing statistics in further maths. So let's have a look at a few more bits like this. The geometric distribution, and what in it is it? Well, it's to do with the kind of thing that you get when lots of board games, if you're ever playing a game and you have to roll a 6 before you can start. And obviously you've got a 1 in 6 chance of getting it straight away. But if it's anything like me, when I play these games with my family, I'm always the last one to actually get the 6. I end up rolling it lots and lots of times. If you just think about the maths, if I'm going to get on my second go, that means I've got to have failed first time, and there's quite a large chance of failing first time. It's 5 out of 6. And notice the times, I then have to get it straight away on the second go. So it's 5/6 times 1/6. If I'm going to get on my third go, that means I will fail twice, but then succeed on my third time. So that should really say, I'm just noticing it's slightly an error here. So I fail once, I fail twice, and then, so it really should say 5/6 times itself. So I'm going to put that in a bracket straight away. And then you fail twice, and then you get your success, and the 1 out of 6 is your successful go. On that basis, then we have the beginnings of a formula. I think this starts looking like a formula, but we must make some assumptions first. We assume that every time you do the trial, that your probability of success is constant. Now, if I'm rolling a dice, that seems quite reasonable. Each trial is independent of all other trials. Again, if you're tossing a coin or rolling if you're doing natural things which are probability based, picking a card from a pack, these are all definitely equally likely outcomes. In one event doesn't affect the other events. Each trial is selected at random. That seems fine. Yeah, I'm not purposely making 4s come up or something like this. So these 3 rules are perfectly reasonable. Notice though, if I'm trying to model real events, it might be, for instance, I don't know, I'm taking penalties, I'm shooting at a goal, and perhaps I'm not very good at scoring. I might have a probability, for instance, of scoring on my first go of 0.4, maybe 0.3. And that means I'm going to have to keep on taking these penalties until eventually I score. Now, I suppose if I'm taking penalties, is the probability of success constant every time? 0.4 every time, 0.3, whatever you decide it is. Possibly. Are they independent trials? I.e., will the fact that I've just put it to, I don't know, I had my penalty saved, where I struck the ball straight down the middle and the goalie saved it. Is he going to stay there? Am I going to shoot there? All things might now change. So in reality, with real life situations, some of these rules, some of these assumptions might be a bit dodgy. A couple of examples then, in addition to the ones I made up just then. One example of a geometric distribution is an event repeated lots and lots of times until a certain outcome occurs, and it might be rolling a die until we get a 6. That was the one I had in the example. A second example might be one in which we try to model a situation in which a student has to do an exam until she eventually passes. So you can see she takes the exam. It might be a driving test, for instance. She takes the exam, she fails. She takes the exam, she fails. She takes the exam. Yeah. What's the probability it's your pass on their fourth go, for instance? And in the obvious example, problem the example I just done, again, is does this second example have a constant probability? Is each event independent even? The student, you would hope, would be getting better and better each time she does the exam. We hope. So an example then of this would be something like this. A darts player must end the game by throwing the double. The probability of doing so, we are told, is 2/5. So I'm told that P, the probability of success, is 2/5. He keeps throwing darts until he hits a double. Describe the distribution. Well, I would describe this as X is geometric. Notice the way it's written. And you then just put in brackets the probability of success. You just write 2/5. So that's really nice. What assumptions have I made? Well, I've made those same three assumptions that I wrote down before. I've got random events, random, independent events, and what's the third one? The third one was constant probability. Now, the one problem with what I've just done is that really we should reference the darts constant probability of getting a double. So try to put it into context. And into context basically means reference the situation that you're talking about. Now, this is where I want to show you how to use a calculator. What's the probability he needs exactly 5 throws? So if I just go through this, this is what the calculator tells us. It says we can only use the normal and binomial distributions on the other calculator. That's why we're using this. Yes, I'm happy with that. Now, you're going to have to press this second button, and then that distribute button that I showed you at the outset. And when you do that, I personally always go up, but you can go down. Doesn't matter which way you go. Up's quicker. So when you do that, you press the second function distribute, and you go up, and it's immediately on geometric PDF and geometric CDF. You can see them there. Now, one of them does exactly equal to's. So for questions that ask for x is equal to some number, you press the PDF. This is the same as we've seen on binomials. And if it wants a less than, and notice this is only for a less than, we do geometric CDF. So if we want for greater than or equal to, if we get asked a question, probability x is greater than or equal to, in fact, this E is like that, greater than or equal to 8. Now we would have to, on this one, reverse it like we did with the binomial and do x is less than or equal to 7. And do 1 minus that answer. Notice, by the way, here is question C, and it says for C, exactly 5 throws. So it's definitely this one, because it's an exact one, x equals something. And we're going to press geometric PDF. And what you have to type in, now there's a couple of different ways of doing this, but you've got to somehow tell it your probability, comma, tell it your how many you want it to be. And here it says exactly 5 throws. So we have to enter those. Now the calculator, some calculators you type it in like that, and some of the newer calculators with the newer software, it actually physically asks you. So when I type it on mine, let's just do it on mine, it comes up x value and p. Oh, in fact it says p first, so I'd have to type in 2/5, which is 0.4, x value of 5, and then it says paste, and then you can type it in, and you'll notice it comes up, well, 2/5 or 0.4, comma 5. And when I do that, it should then give me the answer. And I get, when I've done this, since this is the question, I get 0.05184. So that's nice. At most 2 throws, that's a posh way of saying what's the probability that it will happen in less than or equal to 2. Look out for this, at most. So again, to do this, I'm going to press the geometric CDF button. So clear your screen, second function distribute, go up to the geometric CDF. So I've got that on my screen. P is still 0.4. My x value is still, well, no, my x value is now 2, I nearly said 5 then, and paste that in and press enter. 0.64. So it's exactly 0.64 according to this. At least 8 throws, and I've already told you how to do this. We're going to have to do the 7. So this will equal 1 minus some answer, which I'm going to do. So I'm going to go back to geometric CDF. and I've got 0.4 in, and I'm going to have to type in 7 into the x value and paste, and this there, so it's 1 minus 0.9720, which sounds to me like 0.0280. I think that's probably right. Between 3 and 7 inclusive basically means I want the 3 and I want the 7, so this is the probability that x is between 3 and 7. Notice I'm showing that I can be equal to both. Now to do this, it's the probability that x is less than or equal to 7 minus the probability that x is less than or equal to, well, I want the 3, so I've got to go under it, 2. So if I do that here, in fact I'll do it on the next slide, probably got a bit more room yet. So the probability of less than or equal to 7, actually I just got that on my screen, that's handy, it's 0.972064 it actually says. I've written it all down, don't think I need it all, but and then I do the same thing again, but this time with 2. So geometric CDF 0.4, x value is 2, paste that in. Obviously different calculators. Or was that the 0.64 we had before? It probably was. And therefore I can do that. I can do the 0.972064 minus my answer, and I get 0.33. 2. Yeah, I knew I didn't need all that detail. So what my answer is, oh, interestingly, I've done it to 4dp here, but I didn't need it. 518. Is that what I got? 518, yes, I did 5184 there. 0.64, 0.280, and so yes, all of those are right. Constant probability, independent throws, and random as well, I suppose. Now, look, there is a formula for this. This is in the formula book, the OCR AS Further Maths formula book, and also the A-level formula book. You get all of this. So this comes from this idea that you fail lots of times, but on your last go you get it. So if I want to do it after x goes, I failed x minus 1 times. Now notice there's also these two formulas, one for the expectation and one for the variance, and you will be asked stuff about those as well. And I've got a couple of formulas here. To be honest, I never use these. I just use the calculator whenever possible. So let's do a question. This is, suppose we have a random variable. Write down, we do this until we get a 3 is thrown. So x is geometric, and the probability of getting a 3, I'm assuming is a 6th, because it probably says it's a fair die. It doesn't actually, but I'm assuming it is. Find the probability that x is greater than that. Well, I know that is 1 minus the probability that x is, I want 5. So less than or equal to 1 less than it, 4. So let's type that in. Geometric then, using the buttons, it's a CDF. What's my probability again? It's 1/6, so I'm literally writing 1 divided by 6. And x value is 4. Paste that in, and I get, well, it's 1 minus, obviously, what do I get? 0.5177, which sounds like 0.4823. Find the expected number of throws. Well, again, this is my expected number of throws, sometimes called the mean, and it's mu, and it's just 1 divided by p. So it's 1 divided by, what was it? It was probability was 6. Oh, 1 divided by 6. Well, if you do that on your calculator in your head, the answer is 6. And that's not surprising to be told. We expect to take 6 goes to get a 3. Find the variance. Well, the variance sigma squared is 1 minus p, which is 1 minus a 6th, divided by p squared, which is a 6th squared. You can type it into your calculator, or you can try to do it in your head. That's divided by a 36th. And that means I turn it upside down and I multiply. You might remember that. I reckon that's 30. Is that right? Yes, it is. It is 30. So, yes. And everything else is, yes, is right. And we've got one example there. I'm going to save this to the lesson. I always like to save something. And that I think that will fit in quite nicely. We'll worry about the answers in lesson. But there you are. This is what we're going to do in lesson exercise 2E. I think it's quite a nice little topic.